Okay, next on our agenda is the soft actor critique algorithm. This is a state-of-the-art deep reinforcement learning algorithm that we are going to cover today. This algorithm is a type of an actor critique algorithm. It uses function approximation, deep neural networks specifically, both for the actor and the critique. The actor is a policy, is a soft policy that produces a distribution over the action, while the critique is a Q network, learning Q values. However, it's not really a critique in the general sense that we've seen previously, because these Q values are not defined specifically for the current policy that is used by the actor. These are actually, or it tries to converge on the optimal, on Q star values. So in that sense, some people say that this is not exactly an actor critique algorithm because the critique is not criticizing the actor. But it follows, again, similar lines to previous actor critique algorithms. Interestingly, we will not use the policy gradient theorem here. We'll have a different way to update our actor, the policy in our actor, and we'll define that. And of course, this is a deep RL algorithm, actually one of the state-of-the-art deep RL algorithms. So to begin with, we'll need to define entropy. So entropy in the general sense, it's a term that comes from the physics domain. We will look at entropy as the lack of order or predictability. It's a gradual decline, so the increase in entropy is a gradual decline into disorder. But we'll define it for a specific static system, and we'll see how it evolves over time in our settings. So let's look at an example of what entropy is and why do we tend to see high entropy state, that is a lot of disorder in real-world processes. So for instance, let's look at the deck of cards, and let's try to answer the following question. What is the probability of getting a specific order of cards after shuffling a deck?
There's 52 cards, so it'd be 52 factorial. 52
factorial, one probability is between 0
1 by 52?
Right, so we have one specific order out of 52 factorial orders, and so indeed, if we perform random shuffling of the card deck, the probability of obtaining a very specific order is 1 over 52 factorial, which is a very, 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 very low probability, right? But normally we don't care about a specific state, a specific order, and I can ask, what is the probability of getting a configuration of cards where cards are ordered based on value, right? And so in that case, it's not a specific order because they have different colors and shapes. I don't care about exactly which color, I just want the specific order according to the values. So what's the probability of that? The number of such configuration, I'm not sure, again, it depends on how do we define the specific...
Might be 13 factorial, not sure.
Maybe. In any case, it will be the number of configurations that align with our request over 52 factorial, right? And so you can ask, why is it not probable to shuffle cards and get ordered values? Because, well, it's still a very low probability, right? It might be, we might have 1,000 such configurations. We don't care about the permutation of the, let's say, of the shapes, but it's still over 52 factorial, right? So at the end of the day, it's a very low probability. So in most cases, when we randomly shuffle a deck of cards, we get truly no specific order. Why? We didn't have a higher probability of achieving that very specific order. It's just that there are much more permutations where there's no specific order, right? So this order is the most likely situation in most cases, right? This also applies if you have molecules traveling random in a room, so the same logic can be applied. That's actually what physicists usually refer to, right, as entropy. And indeed, the second law of thermodynamics states that, so this discusses the evolution of entropy in a system. That's the second law of thermodynamics. It states that the total entropy of an isolated system can never decrease over time. That is, isolated systems spontaneously evolve towards thermodynamic equilibrium. That is, the state with maximum entropy. Okay, the most disordered state. So, again, as a simple example, you can think of if we clump together many particles and they have some random movement to them, and so over time they will tend to disperse. Not because they are not able to, at some point, maybe reach a state where they're all clumped together again, but it's just that it's very improbable. And it's much more probable to have states, considerably more probable to have states, to evolve to a state where they are all sparsely distributed outwards. And interestingly, we can tie this phenomena also to the discipline of information theory. Because for any even physical system, you can ask yourself how much information is required in order to store the exact state of this physical state, right? For instance, if we have these particles, and let's say I have a grid here with Planck lengths, so the particles can be in either one of these cells. And we would like to have a state representing where all of the particles are at any given moment. So you can see that it doesn't require a lot of bits to represent this state, right? The state here on the right, where all the particles are in the same location. How many bits would I require? Say, for instance, I have 9 states.
9 into 8.
So probably in this case, I'll only need to be able to represent 1 out of 9 locations, right? I just need to say, hey, this is in location, I don't know what the indexes are, but it's in the middle cell, right? So that will be very easy. However, if we look at this state here, the high entropy state, you can see that now you need a lot more information in order to represent this state, or to be able to describe this state to someone, well, that doesn't see the state. Specifically, if you care about the exact particles, where, if the particles are not interchangeable, you need a lot of bits to represent this information, right, compared to that information. So you can see that high entropy physical states also require a lot of data, a lot of bits, information bits, in order to represent them. And indeed, this helps us to define entropy in information theory, where information generally is a way for us to answer questions, right? It can be done with bits, for instance. The more uncertain we are about the answer initially, the more information exists in the answer, right? For example, I have several examples here. So let's say that we would like to answer a Boolean question with prior 50-50, half and half. Right? How many bits will I require in order to transmit this question? I will need 1 bit, right? It's either, the answer is either 0 or 1. How many bits will I need in order to answer a 4-way question with a prior of 0.25 for each one of these? 2 bits, yes, you're right, 2 bits. Almost right, so we'll need 1 bit to say, hey, we're in this region or that region, and then 1 more bit to distinguish between them, these 2. So you can see, hopefully mentally, that you break this down to something like a decision tree, where each bit helps you split the information into 2. So you get, like in the general case, if we have a p-way questions with 1 over p, you can see that we'll need log with a base of 2 of p, of the number of possible answers, right? Because each answer will split it into 2. Okay, but this is just intuition. We'll continue, and of course we'll define it more mathematically. So here we'll need 2 bits. Let's look at a different question. What if we would like to answer a 4-way question with prior 0, 0, 0 and 100% that answer, the final answer? How many bits?
1 bit?
We can probably do with less than that.
0 bit? That's the answer.
That's the answer. There's no.
You don't need a bit to represent that?
So
yeah.
Any answer that I will give will not contain any information. Right? You know the answer. I can't give you more information about this answer. Right? So no bits will help you gain more information regarding this answer. What about the 3-way questions with a prior 1 over 3?
2.
So now I'm asking in expectation. This is a bit of a tricky question, right? So first of all, I can use 1 bit to distinguish between this answer and these two. Okay? Now, for some answer, I will need another bit. In what case?
For some answer, you'll need another bit. Sorry, I didn't understand.
Okay. So let's say that I use 1 bit to tell me whether the answer is this one, is index number 0. Sometimes it is. Sometimes the bit will be on. It will be, yes, this is the answer. I'm done. I only required 1 bit, right? But what will happen if that's not the answer?
Then it could be any of the other 2 bits.
Right.
Any of the other 2 states. Yeah.
Right, and how many bits will I need to distinguish between those?
1.
1 more,
yeah.
right? 1 more to distinguish between these two. So sometimes I will need only 1 bit to answer this question, but sometimes I will need 2 bits. What's the probability of me needing to have 2 bits to answer this question?
It would be 1 by 3.
1 by 3, I'll be able to answer the question with a single bit.
2 by 3.
2 by
That I wouldn't, yes.
Yes.
2 would, yes.
Okay, so indeed, in any case I need 1 bit, and then in 2/3 of the cases, I will need an extra bit. So in expectancy, I will need 1 and 2/3 bits. What if we would like to answer a 3-way question with a prior half, and then quarter and a quarter?
That would be 1 bit plus another 2 bits again.
With what probability will I need 2 bits?
So, with what probability? Half?
Right. So on expectancy?
So, in expectancy, 1.5.
1.5, yeah, that's right, okay. Great. So this is the general idea behind entropy in information theory. And so, for instance, this is something that I told you intuitively before. If we have a high entropy p-way question, high entropy means that we have a uniform distribution of our answers, right? That would be high entropy. This case would be very low entropy. It's very ordered, so the entropy represents disorder. So this one has a very low entropy, and this one has a high entropy. Okay? And this one is somewhere in the middle. Okay. But if, for instance, we have a uniform distribution, that's the highest entropy, with probability 1 over p for each one of the p-way questions, then, as we discussed before, since you can view this as a binary tree, where each bit helps you split all of the data in 2, then you know that you will need log of base 2 of 1 over p bits. Okay? So, and of course we would like a more general answer for the case where the prior is not necessarily uniform, but you have different probabilities for each one of the possible outcomes. In that case, the information is the expected number of bits, right? As we've seen before, what's the probability that we need 2 bits, that we need 3 bits, and so on. So the expected value over these is, again, it's the expectation of log base 2 of 1 over pi, where p, the answer, is what we take the expectation over. And right, if we use the definition of expectation, this is simply the sum over all possible outcomes of minus the probability of the outcome log base 2 of the probability. So this is also called the entropy of the distribution. The more information is in an answer, the higher the entropy is. The more values in our possible answers, usually the higher entropy is. It doesn't have to be, because we can add more possible answers, but they'll have a probability of 0. But usually more values result in higher entropy. More peaked, that is, if more of the probability is on a specific or several specific values, then the entropy is lower. Right, and we can see some examples here, where this would be a high entropy and
low entropy,
and something in the middle. Yeah, okay. And of course, I'm showing the definition for a categorical distribution, but we can easily extend that to a continuous distribution, right? We'll simply take the integral of p log p over all of possible p's, values of p's. Here it will be continuous, for a continuous distribution. So here is another example, just to see that we understand what's going on. For 2 different distributions, either categorical distributions, we have specific discrete values, or a continuous distribution. This is specifically a Gaussian. And you can see for each of these examples, you have two examples for each of these cases. The orange one, which is a high or low entropy?
high entropy.
High, one second. Well, the orange one is
Low entropy.
Low entropy, right? Because you see it's more peaked. And the blue one is higher entropy, right?